Hello there, and welcome. Tonight I want to take you somewhere quiet, somewhere peaceful, where the weight of the day can finally slip from your shoulders like a silk scarf falling to the floor. Just let yourself settle in, wherever you are right now, and know that for the next while, there's nowhere else you need to be, nothing else you need to do except drift with me through the cosmos toward a mystery that has puzzled astronomers for decades. It's about Venus, our nearest planetary neighbour, and the curious, almost dreamlike way it spins backward through space, turning opposite to nearly every other world in our solar system. It's a question that might seem simple at first, maybe even doubtful, but like all the best mysteries, it opens like a whispering door into deeper physics, deeper understanding, and tonight, deeper calm. Before we begin this journey together, I wonder where you're listening from tonight. Are you tucked into bed in a city where lights still twinkle outside your window? Or perhaps you're in a quiet countryside where the stars themselves are your nightlights. What time is it where you are? Is it that precious hour when the world finally grows still, when even the busiest streets surrender to silence? If this peaceful journey through space feels like the kind of companion you'd like to have on other nights too, you might consider gently tapping that subscribe button, like leaving a bookmark in a favourite book of bedtime stories. And if you feel moved to leave a soft note in the comments, telling us where you're listening from, we'd love to know you're here with us, sharing this quiet moment under the same vast sky. These small connections, these gentle hellos from around our world, remind us that even in our solitude, we're never truly alone in our wonder about the universe. What if, just maybe, Venus's retrograde spin was not an accident, not a cosmic mishap, but a gentle memory of how worlds begin and how they keep time with their skies? What if this backward-turning planet, this world that watches the sun rise in the west and set in the east, holds secrets about the very nature of planetary evolution, about the delicate dance between atmospheres and solid ground, about the way gravity and time conspire to create the rhythms that worlds follow for billions of years? Tonight, we'll explore this together, not with urgency or alarm, but with the kind of patient curiosity that belongs to stargazers and dreamers, to those who understand that the best mysteries are not puzzles to be solved quickly, but stories to be savoured slowly. You see, Venus has always been there for us, a constant companion in our skies, known to ancient civilizations as both the morning star and the evening star, though they didn't always realize these were the same celestial body. The Greeks called it Phosphoros when it heralded the dawn, and Hesperos when it followed the sunset, not knowing they were naming the same world twice. The Romans gave it the name we still use, Venus, after their goddess of love and beauty, perhaps because of how it shines with such serene brightness, outshining everything in the night sky except the moon. And yet, for all its familiarity, for all the thousands of years humans have watched it trace its path across our skies, Venus kept its backward secret hidden until we had the technology to peer through its thick perpetual clouds. As we settle deeper into this story, let your breathing slow, let your muscles relax, and imagine yourself floating gently above Earth's atmosphere, where the blue marble of our home world grows smaller behind us, and the pearl-white sphere of Venus grows larger ahead. Out here, in the profound silence of space, there's no rush, no schedule to keep. Time itself seems to stretch and soften, becoming something more like a suggestion than a rule. We have all night to explore this mystery, to turn it over in our minds like a smooth stone worn perfect by cosmic tides, to let it reveal its secrets one gentle layer at a time. The journey to understanding Venus's backward rotation begins not with the planet itself, but with understanding our place in the vast theatre of space and time. When we look at Venus, we're looking at a world that formed alongside Earth about 4.5 billion years ago, from the same swirling disk of dust and gas that gave birth to all the planets in our solar system. In those early days, the solar system was a very different place, a chaotic nursery where young planets collided and merged, where the rules that would govern their futures were still being written in the language of gravity and momentum. Perhaps it's here, in this ancient history, that we'll find the first whispers of why Venus chose to turn the other way. But I'm getting ahead of myself, aren't I? Let's slow down, let's breathe together for a moment. In through the nose, feeling the cool air fill your lungs, and out through the mouth, releasing any tension you've been carrying. That's it. We have time. We have so much time. The universe has been turning for nearly 14 billion years, and it will keep turning for billions more. Our little exploration tonight, our gentle wandering about Venus and its mysteries, is just a tiny moment in that vast expanse, but it's our moment, and there's something beautiful about that, isn't there? Think about this. Every second that passes, Venus rotates just a tiny bit in its backward direction, so slowly that if you were standing on its surface, you would need to wait the equivalent of 243 Earth days to see one complete sunrise to sunrise. That's longer than Venus takes to orbit the Sun, which means a day on Venus is actually longer than its year. Can you imagine that? A world where a single day outlasts the planet's journey around its star. It's like a cosmic meditation, a planetary practice in the art of taking things slowly, of refusing to be rushed even by the fundamental forces that govern celestial mechanics. This backward, leisurely rotation is called retrograde rotation in astronomical terms, and Venus shares this distinction with only one other planet in our solar system, Uranus, though Uranus has its own peculiar story, rolling on its side like a cosmic barrel. But Venus stands almost upright, dignified in its bearing, simply choosing to turn the opposite way from Earth, from Mars, from Jupiter and Saturn and Neptune, from almost everyone else in our solar neighbourhood. It's as if Venus heard the music of the spheres and decided to dance to its own rhythm, a slow waltz while everyone else was quick-stepping. Scientists have been puzzling over this for decades, ever since we first managed to pierce through Venus's thick atmospheric veil with radar signals and discover the direction and speed of its rotation. Before that, before we had the technology to see through those perpetual clouds, we could only guess at what lay beneath. Some imagined tropical jungles, reasoning that clouds meant water and warmth meant life. Others pictured vast oceans, perhaps with islands dotting the surface like scattered jewels. But when we finally saw through to the surface, we found something else entirely. A world of vast volcanic plains, of highland regions that might be analogous to Earth's continents, and of course that mysterious backward spin. The thick atmosphere that hid Venus's surface from us for so long is itself part of the mystery. It's composed mostly of carbon dioxide, with clouds of sulfuric acid droplets, and it's so dense that the pressure at the surface is about 90 times what you'd feel at sea level on Earth, equivalent to being nearly a kilometre underwater. This atmosphere doesn't just hide the surface, it interacts with it in complex ways that we're only beginning to understand. The atmosphere superrotates, meaning it circles the planet much faster than the planet itself rotates, completing a circuit in just 4 Earth days while the solid planet below takes those 243 days to turn once. It's like watching clouds race across a nearly motionless landscape, a kind of atmospheric river flowing endlessly around a world that barely seems to notice. Perhaps this is where we begin to find clues to the backward rotation mystery. You see, when you have such a massive atmosphere moving so quickly over such a slowly rotating planet, there are forces at work, subtle pushes and pulls that, over millions and billions of years, might influence how the planet spins. Imagine the atmosphere as a kind of brake, or perhaps more accurately, as a partner in a very slow, very patient dance, where each partner influences the other's movement over cosmic timescales. The Sun plays a role too, of course. Its gravity tugs at Venus constantly, not just pulling it along its orbital path, but also creating what scientists call tidal forces. These aren't tides like we have in Earth's oceans, but rather subtle deformations in the planet itself, bulges that the Sun's gravity raises in Venus's rocky body. As Venus rotates, these bulges move, and the Sun's gravity pulls on them, creating a torque, a twisting force that, over eons, can change how a planet spins. On Earth, similar forces from the Moon are gradually slowing our rotation, making our days incrementally longer, though the change is so slight you'd need millions of years to notice without precise instruments. But Venus has no large moon to influence its spin, no celestial companion to help stabilize its rotation the way our moon does for Earth. Instead, Venus dances alone with the Sun, and perhaps that solitary dance, combined with the peculiar properties of its thick atmosphere, led to its current backward state. Some scientists have proposed that Venus might have started out rotating in the same direction as Earth and the other planets, but that over billions of years, the combined effects of solar tides and atmospheric friction gradually slowed its rotation to a stop and then reversed it. It's a beautiful thought, isn't it? A planet that turned so slowly it forgot which way it was going and simply started turning the other way. There's another possibility too, one that speaks to the violent early history of our solar system. Perhaps Venus was struck by a massive impact, something large enough to flip its rotation or knock it into a different spin state. We know such impacts happened. Earth itself was likely struck by a Mars-sized body that created our moon, and Uranus was probably knocked onto its side by a similar collision. But if Venus suffered such an impact, it left no obvious moon as evidence, no celestial witness to testify to the violence of that ancient encounter. Instead, we're left to read the clues in the planet's present state, in its backward spin and its moonless sky. As you lie there listening, perhaps you can feel Earth rotating beneath you, that steady eastward turn that carries us from night into day and back again every 24 hours. It's a rhythm so fundamental to our existence that we rarely think about it, yet it governs everything from our sleep cycles to our weather patterns. Now imagine if Earth suddenly started rotating the other way. The sun would rise in the west and set in the east. The patterns of winds and ocean currents that we've known for all of human history would reverse. Weather systems would move in opposite directions. It would be the same planet made of the same rock and water and air, but it would be profoundly different in ways that would ripple through every aspect of life. This is the reality that Venus lives every day, if we can call those long Venus days days in any meaningful sense. On Venus, the sun rises in the west, though you'd never see it through those thick clouds, and it sets in the east 117 Earth days later. The surface experiences daylight for nearly 2 months straight, then darkness for another 2 months. It's a rhythm so different from our own that it challenges our very conception of what a day means, what patterns a living world should follow. But here's something wonderful to consider. Venus's backward rotation might not be a flaw or an accident, but rather a kind of equilibrium, a stable state that the planet settled into over billions of years of subtle adjustments. Some scientists have calculated that Venus's current rotation rate might be in what's called a resonance with its orbit, a mathematical relationship where the forces trying to speed it up and slow it down have reached a perfect balance. It's like a pendulum that has found its natural rhythm, swinging back and forth in harmony with the forces acting upon it. This idea of resonance appears throughout the solar system. Mercury, the innermost planet, rotates 3 times for every 2 orbits around the Sun, locked in a 3.2 resonance that keeps the same regions facing the Sun at every other closest approach. Jupiter's largest moons are locked in resonances with each other, their orbital periods forming simple mathematical ratios that create a kind of celestial choreography. Perhaps Venus's backward rotation is just another example of this cosmic tendency toward mathematical harmony, a solution to the complex equation of forces that act upon it. The more we learn about Venus, the more we realize how much we still don't know. Every spacecraft we've sent there has revealed new mysteries alongside the answers it provided. The Soviet Venera missions, those hardy pioneers that were the first to land on Venus's surface, survived only minutes or hours in the crushing pressure and searing heat. But they sent back images of a rocky, desolate landscape that looked almost familiar, like a desert on Earth if you could ignore the orange-tinted sky and the knowledge that the temperature was hot enough to melt lead. The Magellan spacecraft, orbiting Venus in the 1990s, used radar to map nearly the entire surface, revealing a world of volcanic features, rift valleys, and mysterious circular structures called coronae that might be unique to Venus. More recently, the European Space Agency's Venus Express and Japan's Akatsuki spacecraft have studied Venus's atmosphere in unprecedented detail, watching the clouds swirl and flow, tracking the superrotation, and discovering new mysteries like the strange dark patches that appear and disappear in the ultraviolet images of the cloud tops. These missions have shown us that Venus is not a dead world but a dynamic one, with possible active volcanism and an atmosphere that's constantly changing in ways we're still trying to understand. And here's something that might surprise you. Despite all its differences, despite the backward rotation and the crushing atmosphere and the surface temperature that could melt spacecraft, Venus might be the planet that best helps us understand Earth's future. You see, Venus might once have been much more Earth-like. Some scientists believe it could have had oceans of liquid water billions of years ago, before a runaway greenhouse effect boiled them away and created the hellish conditions we see today. By studying Venus, we're looking at one possible future for Earth, a cautionary tale written in clouds of sulfuric acid and an atmosphere thick with carbon dioxide. But tonight, we're not here to worry about such futures. We're here to wonder, to explore, to let our minds drift among the stars while our bodies rest. The story of Venus's backward rotation is not a story of catastrophe, but of patience, of forces acting over timescales so vast that mountains rise and fall while the planet makes its slow adjustments. It's a reminder that the universe operates on rhythms far removed from our human urgency, that there are clocks keeping time in ways we're only beginning to perceive. As we continue our journey toward Venus, floating through the velvet darkness between worlds, consider how perspective changes everything. From Earth, Venus appears as a bright point of light, beautiful and serene, giving no hint of its backward nature or its hostile surface. From space, it's a pearl-white sphere, its clouds reflecting sunlight with an albedo that makes it one of the brightest objects in our sky. But beneath those clouds lies a world that challenges our assumptions, that reminds us that planets, like people, can follow their own paths, their own rhythms, even when everyone else is going the other way. The ancient astronomers who first tracked Venus's movement across the sky noticed something peculiar about its behaviour. Unlike the outer planets, which can be visible all night long when they're in the right position, Venus never strays far from the sun in our sky. It's always a morning or evening star, never a midnight wanderer. This is because Venus orbits closer to the sun than Earth does, so from our perspective, it can never appear opposite the sun in the sky. Those ancient observers didn't understand the reason for this behaviour, but they documented it carefully, building up centuries of observations that would eventually help later astronomers understand the true nature of our solar system. Today, we have advantages those ancient astronomers could never have imagined. We can send robotic emissaries to Venus, we can bounce radar signals off its surface, we can study its atmosphere with spectrometers that reveal its chemical composition. And yet, for all our technology, for all our sophisticated understanding of physics and chemistry, Venus still keeps some of its secrets. We still don't know for certain why it rotates backward. We still don't fully understand the complex dynamics of its atmosphere. We still wonder about its interior structure, about whether it has plate tectonics like Earth, or a more static surface like Mars. These uncertainties might seem frustrating if you're the kind of person who needs immediate answers, but there's something beautiful about mysteries that persist despite our best efforts to solve them. They remind us that the universe is larger and more complex than any single human mind can fully grasp, that there will always be new questions to ask, new wonders to discover. Venus's backward rotation is just one thread in the vast tapestry of cosmic mysteries, but it's a thread that, when pulled, reveals connections to fundamental questions about how planets form, how they evolve, and how the various forces in the universe balance against each other. Think about the forces at work here for a moment. There's gravity, of course, the fundamental attraction between masses that keeps Venus in orbit around the Sun and holds its atmosphere close to its surface. There's the electromagnetic radiation from the Sun, heating the atmosphere and driving chemical reactions in the clouds. There's friction, as that thick atmosphere drags against the surface below. There's the planet's own internal heat, left over from its formation, and possibly supplemented by radioactive decay in its interior. All of these forces interact in complex ways, creating feedback loops and resonances that we're only beginning to map out. In some ways, trying to understand Venus's backward rotation is like trying to understand a piece of music by looking at the individual notes. You can identify each component, measure its frequency and amplitude, but the music itself emerges from the relationships between the notes, from the patterns and rhythms that they create together. Venus's rotation is the result of billions of years of these cosmic forces playing together, creating a planetary symphony that happens to be in a different key from Earth's familiar tune. As we float here in our imagination, approaching Venus through the darkness, let's take a moment to appreciate the sheer scale of what we're contemplating. Venus is nearly the same size as Earth, just slightly smaller, with a diameter of about 12,100 kilometers compared to Earth's 12,742. That might not sound like much of a difference, but it means Venus contains about 860 million cubic kilometers of rock and metal, a sphere of matter so vast that if you could drive a car around its equator at highway speed, without stopping, it would take you more than 2 weeks to complete the circuit. And all of that mass, all of those quintillions of tons of rock, are rotating backward once every 243 Earth days, a momentum so enormous that it would take an almost unimaginable force to change it significantly. Yet forces are acting on it, have been acting on it since the day it formed. Every photon of sunlight that strikes Venus's clouds imparts a tiny push. Every molecule of atmosphere that flows from day side to night side carries momentum. Every slight deformation of the planet's shape due to the sun's gravity creates a torque. These forces are infinitesimal compared to the planet's enormous rotational inertia, but given enough time, even the smallest force can move a world. This is one of the profound lessons of planetary science. Time changes everything. Mountains that seem eternal on human timescales are temporary bumps on geological timescales. Oceans that define the very character of our world are fleeting features on planetary timescales. And rotation rates that seem fixed and immutable can reverse themselves given enough eons. Venus's backward rotation is a testament to the patient power of time and physics working together. But let's bring our focus back to the present moment, to this quiet time we're sharing, as we contemplate Venus and its mysteries. Right now, as you listen to these words, Venus is out there, turning its slow backward turn. If it's the right time of year and you're in the right location, you might even be able to see it, shining brilliantly in the morning or evening sky. That light left Venus's cloud tops just minutes ago, travelling across the millions of kilometres that separate our worlds, carrying with it information about that distant planet's atmosphere, its temperature, its composition. When we look at Venus, we're looking at a world that might have started out very much like Earth. Similar size, similar mass, similar distance from the Sun, at least relatively speaking. If you could somehow swap Earth and Venus's positions in the early solar system, who's to say which would have become the living world and which the greenhouse inferno? Perhaps it was just chance, just the random variations in how planets accumulate their atmospheres and develop their climates that led to such different outcomes. Or perhaps there's something more fundamental at work, some principle we haven't yet discovered that determines why one world becomes a paradise and another becomes a paradise lost. The question of Venus's habitability, past or present, adds another layer to our mystery. If Venus once had oceans, as some scientists believe, then it must have rotated differently in the past because the current slow, backward rotation would create extreme temperature differences between the day and night sides that would be incompatible with stable bodies of water. Unless, of course, the thick atmosphere we see today developed later, after the oceans were lost, creating the global greenhouse that now keeps the entire planet at nearly the same temperature, regardless of whether it's in sunlight or darkness. There's even speculation, tantalizing but unproven, that life might exist in Venus's clouds today. Not on the surface, where the temperature and pressure would destroy any known form of life, but high in the atmosphere, where conditions are more temperate. There are layers in Venus's atmosphere where the temperature and pressure are similar to Earth's surface, where water droplets exist, where chemical energy is available. If life exists there, it would be unlike anything on Earth, adapted to perpetual flight in an acidic environment. But life has surprised us before with its ability to thrive in seemingly impossible places. Imagine for a moment that there is life in Venus's clouds, microscopic organisms that have never known solid ground, that live their entire existence floating in the eternal winds of the super-rotating atmosphere. For them, Venus's backward rotation would be irrelevant. Their world would be defined by the 4-day cycle of the atmospheric superrotation, not the 2 from 43-day rotation of the invisible surface far below. They would know day and night, but on a schedule completely different from the planet's actual rotation, living in a layer of reality separate from the solid world beneath them. This is pure speculation, of course, but it illustrates how Venus challenges our Earth-centric assumptions about what a planet should be, how it should behave, what kinds of existence it might support. Venus's backward rotation is just one aspect of its alien nature, but it's the aspect that perhaps best symbolizes how different worlds can be, even worlds that started from the same cosmic ingredients in the same stellar neighborhood. As we've been talking, as we've been floating here in our minds between Earth and Venus, both planets have continued their rotations, Earth spinning eastward, carrying you through space at hundreds of meters per second depending on your latitude, while Venus turns its slow westward turn, patient and unhurried. Both planets are also orbiting the Sun, Earth at about 30 kilometers per second, Venus slightly faster at 35 kilometers per second due to its closer position, and our entire solar system is moving too, orbiting the center of the Milky Way galaxy at over 200 kilometers per second, carrying all the planets, including backward spinning Venus, on a journey that takes over 200 million years to complete. When you think about all these motions, all these rotations and revolutions happening simultaneously at different rates and in different directions, it becomes clear that there's no absolute reference frame, no cosmic stage that stays still while everything else moves. Motion is relative, rotation is relative, and perhaps Venus's backward spin only seems backward because we're comparing it to our own forward spin. From Venus's perspective, maybe we're the ones rotating backward. In the quiet depths of space, distances unfold like slow tides, and time stretches into a kindly horizon where past and future blend into an eternal present. If we compressed the age of the cosmos into a single day, starting at midnight with the Big Bang, the first stars wouldn't light up until about 5 minutes past midnight. The Milky Way galaxy wouldn't form until around 3 a.m. Our solar system, including Earth and Venus, wouldn't appear until about 4 p.m, when the cosmic day was already 2/3 over. Life on Earth would emerge around 5:30 p.m, but it would remain microscopic and simple until well after 9 p.m. The entire history of complex life, from the first multicellular organisms to today, would fit into the last 2 hours before midnight, and human civilization. All of recorded human history would flash by in the last fraction of a second before the clock strikes 12. In this compressed cosmic day, Venus has been rotating backward for about 8 hours, since 4 p.m. when it formed. That might seem like a long time, but remember, the universe has been expanding and evolving for 24 hours in our metaphor. Venus's backward rotation is neither new nor ancient on cosmic scales. It's middle-aged, like the planet itself, settled into its rhythm billions of years ago, but still young compared to the universe as a whole. Perhaps you and I are small in this vast temporal landscape, brief flickers of consciousness in a cosmos that measures time in billions of years. But we are threaded into the fabric, connected to every atom that has ever existed, including those that make up Venus and its backward-spinning bulk. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all were forged in the hearts of stars that lived and died before our solar system was born. We are not separate from the cosmos. We are expressions of it, momentary arrangements of matter that have developed the remarkable ability to wonder about other arrangements of matter, like Venus. Consider the possibility that our questions, spoken gently into the night, are themselves part of the universe learning its own name. When we wonder why Venus rotates backward, we're not just satisfying idle curiosity, we're participating in the cosmos's own self-discovery. Through our eyes, the universe observes itself. Through our minds, it contemplates its own mysteries. Through our questions about Venus's rotation, it explores the range of possibilities inherent in its own physical laws. This is a profound thought, isn't it? That consciousness, wherever and however it arises, might be the universe's way of understanding itself. And if that's true, then our gentle wondering about Venus tonight is not separate from the cosmic story, but an essential part of it. We are the universe asking itself, why does that part of me over there spin backward while this part of me here spins forward? It's a question that emerges from the same physical laws that govern the rotation itself, a kind of cosmic self-reflection that requires both the phenomenon and the observer to be complete. Time, as we experience it, flows in one direction, from past through present to future. But the laws of physics that govern Venus's rotation are mostly time-symmetric, meaning they work the same way running forward or backward. If you could film Venus rotating and play the film in reverse, the reversed motion would still obey all the fundamental laws of physics. This time, symmetry in physical laws makes Venus's backward rotation less of an anomaly and more of an equally valid solution to the equations that govern planetary motion. Yet we experience time as flowing in one direction, and this gives us a unique perspective on Venus's rotation. We can remember when we didn't know Venus rotated backward, we can learn about it in the present, and we can anticipate future discoveries about it. This temporal awareness, this ability to connect past, present, and future in our consciousness, allows us to see patterns and ask questions that the universe, without conscious observers, could never ask about itself. In the grand scheme of cosmic time, Venus's backward rotation might be temporary. Given enough billions of years, the forces acting on it might slow it further, perhaps even stop it entirely, leaving it tidally locked with one face always toward the Sun, like Mercury's near resonance or the Moon's lock with Earth. Or perhaps other forces will maintain its backward spin indefinitely, a cosmic rebel that never conforms to the common direction. We won't be around to see the outcome, but we can imagine it. We can calculate the possibilities. We can add our small contribution to the universe's self-knowledge. The atoms that make up your body right now have been on their own incredible journeys through time. Some were part of the Earth from its beginning, cycling through rocks and oceans and atmosphere for billions of years. Others might have arrived more recently, delivered by comets or meteorites. And before they were part of Earth, they were part of the nebula that formed our solar system, and before that, they were forged in stars or even in the Big Bang itself. You are a temporary arrangement of these well-travelled atoms, a pattern that emerged from chaos, and will return to it. But for this moment, for this quiet night, you are here, conscious, wondering about Venus. When we think about Venus in the context of cosmic time, its backward rotation becomes less of a problem to solve and more of a characteristic to appreciate. Just as every person has unique features that tell the story of their life, every planet has characteristics that tell the story of its formation and evolution. Venus's retrograde rotation is part of its identity, as fundamental to its nature as Earth's blue oceans or Jupiter's great red spot. It doesn't need to be fixed or explained away. It needs to be understood as part of the wonderful diversity of worlds that populate our universe, and what diversity there is. In our solar system alone, we have worlds of ice and worlds of rock, worlds with dozens of moons and worlds with none, worlds with rings and worlds without, worlds that rotate in hours and worlds that take months to turn once. And beyond our solar system, we've discovered thousands of exoplanets, worlds orbiting other stars, and they show even greater diversity. There are hot Jupiters that orbit their stars in mere days, super-Earths that have no analogue in our solar system, and probably countless other variations we haven't yet imagined. In this context, Venus's backward rotation is just one note in a vast cosmic symphony of planetary diversity. Each world has its own rhythm, its own dance, its own way of being a planet. Some of these ways seem familiar to us because they're similar to Earth's way, and others, like Venus's retrograde rotation, seem strange. But strangeness is relative, dependent on what we consider normal, and normal itself is just what we're used to, not what's necessarily common or preferred in the universe. If we could survey all the planets in the universe, would we find that most rotate like Earth, or would we find that backward rotation is equally common? We don't know yet, but as we discover more exoplanets and develop techniques to measure their rotation rates, we'll begin to answer this question. Perhaps we'll find that Venus is unusual, a cosmic outlier. Or perhaps we'll find that retrograde rotation is common, that Venus is normal and Earth is the oddity. Either way, we'll have learned something profound about the range of possibilities inherent in planetary formation and evolution. The search for understanding, this gentle quest we're on tonight, is itself a kind of cosmic force, isn't it? Just as gravity shapes the motion of planets and electromagnetic radiation carries energy across space, curiosity drives the expansion of knowledge, the growth of understanding. Our wondering about Venus's backward rotation is part of this force, a small but real contribution to the universe's ongoing process of self-discovery. Every question we ask, every mystery we contemplate, adds to the sum of cosmic self-awareness. And in this moment, in this quiet exploration we're sharing, we're not just learning about Venus, we're participating in something larger. We're part of the universe's attempt to understand its own complexity, its own possibilities, its own nature. Through us, the cosmos asks, what am I? How do I work? What else might I be? These are not just human questions, they're universal questions, asked through human minds but belonging to the cosmos itself. As we rest in that thought, unhurried, we carry it with us as we glide onward through space and time, approaching Venus with its patient backward turn, knowing that we're not just observers but participants in the cosmic story. We are the universe examining itself, wondering at itself, slowly coming to know itself through billions of eyes and minds scattered across space and time. And tonight, through our gentle contemplation of Venus's retrograde rotation, we add our small voice to that vast chorus of cosmic self-discovery. the fabric of space-time itself, that invisible stage on which all cosmic dramas play out, curves and flexes around massive objects like Venus. Einstein taught us that mass and energy bend space-time, and that this bending is what we experience as gravity. Venus, with its substantial mass, creates its own dimple in space-time, a gravitational well that holds its atmosphere close and defines the orbits of any spacecraft we send to study it. This same curved space-time influences how the planet rotates, creating subtle effects that only become noticeable over millions of years. When we send radio signals to spacecraft orbiting Venus, we can actually measure how the planet's gravity bends space-time by observing tiny changes in the signal's frequency and timing. These measurements have confirmed Einstein's predictions with extraordinary precision and have helped us map Venus's gravitational field in detail. That gravitational field tells us about the planet's internal structure, about how mass is distributed within it, about whether it has a large iron core like Earth or a different internal arrangement. The relationship between Venus's rotation and its internal structure is another piece of our puzzle. A planet's rotation rate affects how material is distributed within it, with faster rotation causing the planet to bulge at the equator and flatten at the poles. Earth, rotating once every 24 hours, has an equatorial bulge of about 21 kilometers. Venus, rotating so much more slowly, is nearly perfectly spherical, with hardly any equatorial bulge at all. This spherical shape means that Venus's gravity field is more uniform than Earth's, which in turn affects how spacecraft orbit it and how its atmosphere circulates. Deep within Venus, beneath the surface we can observe, lies another mystery. Does Venus have a magnetic field generated by a dynamo in its core like Earth does? The answer appears to be no, or at least not a significant one. This absence of a magnetic field might be related to its slow rotation, since the dynamo effect that generates Earth's magnetic field is thought to depend partly on the planet's rotation rate. Without a protective magnetic field, Venus's upper atmosphere is exposed to the solar wind, the stream of charged particles flowing from the Sun, which slowly strips away lighter elements like hydrogen and helium. This interaction between Venus's atmosphere and the solar wind is yet another factor in our backward rotation mystery. As the solar wind strips away atmospheric particles, it carries away angular momentum, potentially affecting the planet's rotation over billions of years. It's a subtle effect, but in the patient arithmetic of cosmic time, subtle effects can accumulate into significant changes. Perhaps Venus's current rotation state is partly the result of billions of years of this gentle atmospheric erosion. We rest in that thought, unhurried, and we carry it with us as we glide onward, ever deeper into the mystery of Venus and its backward turn. Each piece of information we gather, each connection we make, adds depth to our understanding while also revealing new questions, new avenues to explore. This is the nature of scientific discovery. Answers lead to questions, which lead to answers, which lead to more questions, in an endless spiral of expanding knowledge. Now imagine Venus, twin to Earth in size and mass, wrapped in bright reflective clouds that drift and curl like a slow dream across its face. These clouds, so beautiful from a distance, are made of sulfuric acid droplets, a substance that would burn through metal and flesh with equal ease. Yet from space, they appear serene, peaceful, hiding the hellish surface beneath with a veil of white and yellow. Scientists have observed that these clouds circle the planet swiftly, while the surface turns almost imperceptibly, as if time there prefers to linger, to stretch each moment into hours, each hour into days. The clouds themselves are structured in layers, like a cosmic parfait of increasingly dense and hostile chemistry. The uppermost clouds, where the pressure is similar to Earth's surface, are where that superrotation is most dramatic. Here, winds race at speeds of up to 360 kilometers per hour, carrying the cloud tops around the planet in just 4 Earth days. It's a meteorological mystery how these winds maintain their speed, how they're powered, how they've persisted for millions or billions of years. Some force is driving them, some engine we don't fully understand, and that engine might be connected to the planet's slow backward rotation. Below these racing clouds, in the middle atmosphere, the winds gradually slow down, creating a complex pattern of vertical and horizontal circulation. Hot air rises from the sun-heated day side, flows toward the night side at high altitude, cools and descends, then flows back toward the day side at lower altitude. This creates a global circulation cell, a planet-wide conveyor belt of atmosphere that transports heat from where there's too much to where there's too little. On a planet that rotates as slowly as Venus, this circulation is essential for preventing the day side from becoming even hotter and the night side from freezing. Radar maps from spacecraft like Magellan have pierced through these clouds, revealing the surface in remarkable detail. They show us a world of vast volcanic plains, covering about 80% of the planet's surface. These plains are dotted with thousands of volcanic features, shield volcanoes similar to Hawaii's Mauna Loa, pancake domes that have no equivalent on Earth, and strange circular features called coronae that might mark places where plumes of hot material rose from the planet's interior. Some of these volcanoes might still be active today, adding fresh lava to the surface and gases to the atmosphere. The highland regions of Venus, making up the remaining 20% of the surface, rise like continental masses from the volcanic plains. The largest of these, Ishtar Terra in the north and Aphrodite Terra near the equator, are comparable in size to Earth's continents. Ishtar Terra contains Maxwell Montes, the highest mountain on Venus, rising 11 kilometers above the mean surface level. Taller than Mount Everest rises above sea level on Earth. These highlands might be analogous to Earth's continents, but without plate tectonics to move them around, they've remained in the same positions for perhaps billions of years. Patient spacecraft have revealed these features through echoes rather than light, like listening to a shoreline by the pattern of its waves rather than seeing it directly. Each radar pulse sent down through the clouds bounces off the surface and returns slightly changed, carrying information about the texture, composition, and elevation of the ground it touched. By assembling millions of these echoes, we've built up a picture of a world we've never truly seen with our eyes, a map made of sound rather than light. The surface itself, hidden beneath those clouds, exists in conditions that seem almost impossibly hostile. The temperature is around 464 degrees Celsius everywhere, dayside and nightside, equator and poles, a global oven maintained by the greenhouse effect of that thick carbon dioxide atmosphere. The pressure is crushing, equivalent to being 900 meters underwater on Earth. In these conditions, the atmosphere near the surface is so dense it's almost more like a fluid than a gas. If you could somehow stand on Venus's surface, protected from the heat and pressure, moving would feel more like wading through water than walking through air. In this dense, hot environment, even the rocks behave differently than they do on Earth. Some minerals that are stable on Earth's surface would decompose on Venus, while others that are rare on Earth might be common there. The surface rocks are probably basaltic, similar to the rocks that form from lava on Earth, but they're weathered by the sulfuric acid and other chemicals in the atmosphere, creating surface chemistry we're still trying to understand. Some scientists have suggested that the highlands of Venus might be covered with a frost of heavy metal compounds, like lead sulfide or bismuth sulfide, materials that could condense out of the atmosphere at the cooler temperatures found at high elevations. Perhaps the beauty here is not in spectacle but in steadiness, a world that whispers instead of shouts. Venus has no seasons, no ice ages, no dramatic climate shifts, just the same conditions day after day, year after year, eon after eon. It's a world that has found its equilibrium, however hostile that equilibrium might be to life as we know it, and yet, beneath the hush, the axis turns the other way, and that is the wonder we follow, the thread that leads us deeper into understanding. The rotation of Venus affects everything about the planet, from its shape to its climate to its interaction with the solar wind. Because it rotates so slowly, Venus has no significant Coriolis effect, the force that causes hurricanes to spin and helps drive weather patterns on Earth. Without this effect, Venus's atmospheric circulation is simpler in some ways than Earth's, dominated by that single global circulation cell rather than the multiple cells and jet streams that characterize Earth's atmosphere. Yet in other ways, Venus's atmosphere is more complex with waves and vortices we're still trying to understand, patterns that emerge from the interplay of rotation, solar heating, and atmospheric chemistry. At the poles of Venus, the atmosphere forms enormous vortices, swirling clouds that look like cosmic hurricanes when viewed from above. These polar vortices are complex, dynamic structures that change shape on timescales of days, sometimes appearing as single eyes, sometimes as double eyes, sometimes breaking apart into chaotic swirls before reforming. They're connected to the global atmospheric circulation, marking the points where air that has travelled from equator to pole descends back toward the surface. The southern polar vortex in particular has been extensively studied by the Venus Express spacecraft, which watched it evolve over several years. The interaction between Venus's slow rotation and its thick atmosphere creates a phenomenon called atmospheric tides, similar in principle to ocean tides on Earth, but caused by heating rather than gravity. As the Sun heats the day side of Venus's atmosphere, it causes the air to expand and rise, creating a pressure wave that travels around the planet. These atmospheric tides are thought to play a crucial role in maintaining the super-rotation of the upper atmosphere, pumping energy into the winds that race around the planet. They might also influence the planet's rotation rate itself, creating a feedback loop between the atmosphere and the solid planet. Recent observations have revealed another mysterious feature of Venus's atmosphere, a giant wave in the clouds that remains stationary relative to the surface, while the atmosphere super-rotates past it. This wave, stretching thousands of kilometers from north to south, appears to be generated by the interaction between the flowing atmosphere and the topography below, particularly the highland regions. It's as if the mountains of Venus are creating a standing wave in the atmosphere above them, a connection between the solid planet and its gaseous envelope that we're only beginning to understand. The chemistry of Venus's atmosphere is a complex dance of molecules and reactions driven by sunlight, temperature and pressure. In the upper atmosphere, ultraviolet light from the sun breaks apart molecules, creating reactive species that recombine in various ways. Sulfur dioxide from volcanic emissions reacts with water vapor to create the sulfuric acid clouds. Carbon dioxide, the main component of the atmosphere, absorbs infrared radiation and creates the greenhouse effect that keeps the surface so hot. And throughout all these chemical reactions, the atmosphere maintains its super-rotation, its backward circulation relative to the backward rotating planet below. Some of the most intriguing chemistry happens in the middle clouds, where temperatures and pressures are more Earth-like. Here, there are mysterious dark patches that absorb ultraviolet light, giving Venus its distinctive appearance in UV images. We don't know what creates these patches. They could be sulfur compounds, they could be iron chloride, or they could be something else entirely, perhaps even biological in origin. These UV absorbers, whatever they are, affect the planet's energy balance by determining how much sunlight is absorbed versus reflected back to space. And yet, beneath the hush of our limited understanding, beneath the veil of those perpetual clouds, the axis turns the other way, patient and persistent, following its own cosmic rhythm. This backward rotation might seem like a minor detail compared to the dramatic atmosphere and hostile surface, but it's fundamental to everything about Venus. It determines the length of the solar day, the pattern of solar heating, the interaction with the solar wind, and possibly even the long-term evolution of the atmosphere itself. The slow rotation means that Venus's solar day, the time from noon to noon as experienced on the surface, is about 117 Earth days, much shorter than its sidereal day of 243 Earth days. This is because Venus's backward rotation partially cancels out its orbital motion around the Sun. If Venus didn't rotate at all, its solar day would equal its orbital period of 225 Earth days. The backward rotation subtracts from this, giving us that 117-day solar cycle. It's a mathematical relationship that emerges from the combination of rotation and revolution, a cosmic arithmetic that determines the rhythm of day and night on this alien world. Consider this. Most planets spin in one direction, prograde, in the same direction as their orbit around the Sun, and Venus, untroubled, turns the other way, very slowly, as though pausing to remember something important, something from its deep past. Scientists have found that a Venus day lasts longer than its year. It is a tender oddity that invites a closer, kinder look, a puzzle that speaks not of violence or catastrophe, but of patient adjustment over cosmic time. The fact that Venus's day is longer than its year creates a unique situation in our solar system. If you could stand on Venus's surface and observe the Sun, through the thick clouds of course, you would see it rise in the west, climb slowly across the sky for 58.5 Earth days set in the east, and then darkness would last for another 58.5 Earth days before the next sunrise. During this same period, Venus would have completed more than half of its orbit around the Sun. It's a temporal paradox that challenges our Earth-based intuitions about the relationship between days and years. This unusual day-year relationship might have profound implications for any geological or atmospheric processes that depend on solar heating. On Earth, the daily cycle drives weather patterns, erosion, and even biological rhythms. On Venus, with its extremely long solar day, these processes would operate on completely different timescales. The day side has nearly 2 months to heat up, while the night side has nearly 2 months to cool down. Yet the thick atmosphere prevents any significant temperature difference from developing, maintaining that uniform hellish heat through its efficient circulation. It's a question that might seem like a footnote in the grand story of the solar system, but it opens into tides and torques, atmospheres and ancient beginnings. What if, just maybe, this backward spin was not a mistake but a natural balance reached through long, soft exchanges of energy? What if Venus found this rotation state the way a river finds its course, through the patient work of forces acting over millions and billions of years? The concept of tidal locking provides one framework for understanding Venus's rotation. Many moons in our solar system are tidally locked to their planets, always showing the same face, like our own moon does to Earth. This happens because gravitational tides gradually slow a moon's rotation until it matches its orbital period. Venus experiences similar tidal forces from the Sun, but instead of becoming locked with one face always toward the Sun, it might have evolved into a different equilibrium state, one where the atmospheric tides balance the gravitational tides, resulting in the slow backward rotation we observe today. Some scientists have proposed that Venus is in a state called quasi-equilibrium, where various forces have balanced out to maintain its current rotation rate. The Sun's gravity tries to slow the rotation through solid body tides. The atmosphere, heated by the Sun, creates thermal tides that can either speed up or slow down the rotation depending on their phase. The core mantle friction inside the planet dissipates rotational energy, and the solar wind strips away angular momentum from the upper atmosphere. All these forces, acting together over billions of years, might have nudged Venus into its current state. There's something beautiful about this idea of equilibrium, of a planet finding its natural rhythm through the interplay of forces. It's not a static equilibrium, but a dynamic one, with constant small adjustments as conditions change. The atmosphere speeds up and slows down with the seasons, if we can call them that on a planet without axial tilt. The solid planet creaks and adjusts under the stress of tides. The whole system breathes, in a sense, inhaling and exhaling energy in a slow cosmic rhythm. In the silence between stars, between thoughts, between heartbeats, the mystery blooms without urgency. It doesn't demand to be solved immediately. It doesn't threaten or alarm. It simply exists, a characteristic of the universe that we've discovered and are trying to understand. Venus rotates backward, and that's neither good nor bad, neither right nor wrong. It simply is, and in its being, it teaches us about the range of possibilities inherent in planetary existence. The mystery of Venus's backward rotation connects to larger questions about planetary formation and evolution. When planets form from the disk of gas and dust around a young star, they generally inherit the rotation direction of that disk, which is why most planets rotate in the same direction as their orbits. But the details of planet formation are chaotic, with collisions, mergers, and gravitational interactions that can alter rotation rates and directions. Venus's backward rotation tells us that these processes don't always produce uniform results, that there's room for variation, for individuality, even among worlds. Computer simulations of planetary formation have shown that retrograde rotation, while uncommon, can arise naturally from the chaos of the early solar system. Large impacts, gravitational interactions with other planets, or the cumulative effect of many smaller collisions could all potentially reverse a planet's rotation. The challenge is determining which of these scenarios, if any, actually happened to Venus. The evidence has been erased by billions of years of geological and atmospheric evolution, leaving us to piece together the story from the clues that remain. One intriguing possibility is that Venus's rotation was reversed by a resonance between its orbit and rotation, similar to the resonances that govern the orbits of many moons and asteroids. If Venus's rotation rate ever matched certain ratios with its orbital period, tidal forces would have been amplified, potentially pushing the rotation over a tipping point from forward to backward. This wouldn't have been a sudden flip, but a gradual slowing, stopping, and reversal over millions of years, a cosmic pirouette performed in extreme slow motion. Another hypothesis involves the early atmosphere of Venus. If the young Venus had a massive atmosphere early in its history, perhaps even more massive than today's, the atmospheric tides could have been strong enough to significantly affect the planet's rotation. As the atmosphere evolved, perhaps losing mass to space or gaining mass from volcanic outgassing, the balance of forces would have shifted, potentially leaving the planet in the retrograde state we see today. The role of the Sun in Venus's rotation story cannot be understated. The Sun's gravity creates tides in Venus's solid body, just as the Moon creates tides in Earth's oceans. But because Venus has no large moon to stabilize its rotation, it's more susceptible to changes induced by solar tides. Over billions of years, these tides have transferred angular momentum between Venus's rotation and its orbit, gradually modifying both. The current state might represent a balance point where the various torques cancel out, at least approximately. The interplay between Venus's atmosphere and its rotation creates a fascinating feedback system that scientists are still working to understand fully. As sunlight heats the thick atmosphere, it creates pressure differences that drive winds, and these winds carry momentum that can be exchanged with a solid planet through friction at the surface. It's a subtle dance of energy and momentum, played out over geological timescales, with each partner influencing the other in ways that only become apparent when you look at the system as a whole rather than its individual parts. Data reveals the story slowly, like developing a photograph in a darkroom, watching the image emerge from chemical baths of time and patience. Radar echoes from Earth's great dishes at Arecibo and Goldstone have bounced off Venus's surface for decades, each pulse carrying back information about the planet's rotation rate, its surface features, its subtle variations. The Magellan spacecraft's careful mapping revealed not just the topology of Venus, but also hints about its geological history, about the forces that have shaped and reshaped its surface over billions of years. Scientists have observed that thermal tides in the dense atmosphere may softly push the planet's spin, like a persistent, delicate breeze on a sleeping lake. These thermal tides are created by the temperature difference between the day and night sides of the planet, even though that difference is small thanks to the efficient heat transport of the atmosphere. As the atmosphere heats and cools, it expands and contracts, creating waves of pressure that travel around the planet. These waves carry momentum, and when they interact with surface features like mountains or valleys, they can transfer that momentum to the solid planet, potentially affecting its rotation rate over long timescales. The Pioneer Venus mission, arriving at Venus in 1978, was one of the first to study these atmospheric dynamics in detail. It dropped 4 probes into the atmosphere, measuring temperature, pressure, and wind speeds as they descended toward the surface. 1 probe survived the landing and continued transmitting data for over an hour, a remarkable achievement given the hostile conditions. These probes revealed the structure of the atmosphere, the way temperature and pressure increase steadily toward the surface, the chemical composition at different altitudes, and the wind patterns that maintain the superrotation. The Soviet Venera program, a series of increasingly sophisticated missions from the 1960s through the 1980s, provided our first direct observations of Venus's surface. Venera 7 was the first spacecraft to successfully transmit data from the surface of another planet, surviving for 23 minutes in December 1970. Later missions lasted longer and returned the first photographs from Venus's surface, showing a desolate landscape of flat rocks and distant hills under an orange sky. These images, grainy and limited as they were, gave us our first ground truth data about Venus's surface conditions and composition. Venera landers also carried instruments to measure the surface winds, and they found something surprising. Despite the super-rotating atmosphere high above, the winds at the surface are very gentle, typically less than a few meters per second. It's as if the planet's surface exists in a different world from its atmosphere, a realm of stillness beneath the racing clouds. This disconnect between surface and atmosphere is another piece of the rotation puzzle, suggesting that the momentum exchange between atmosphere and surface is more complex than simple friction would suggest. The European Space Agency's Venus Express, orbiting Venus from 2006 to 2014, revolutionized our understanding of Venus's atmosphere and its dynamics. Using infrared instruments that could peer through the clouds at certain wavelengths, Venus Express mapped the temperature structure of the atmosphere, tracked the movement of clouds at different altitudes, and discovered new phenomena like the giant stationary wave mentioned earlier. It also observed how the atmosphere interacts with the solar wind, watching as hydrogen and oxygen are stripped away into space, a slow bleeding of water's components that might have been going on for billions of years. Japan's Akatsuki spacecraft, which arrived at Venus in 2015 after a 5-year delay due to engine problems, has continued this atmospheric surveillance. Akatsuki watches Venus in multiple wavelengths, tracking cloud movements, measuring temperatures, and searching for signs of active volcanism. Its observations have revealed new details about the superrotation, showing how it varies with altitude and latitude, how waves propagate through the atmosphere, and how the mysterious UV absorbers change over time. Each orbit adds to our understanding, like adding brushstrokes to a slowly emerging portrait. These missions have shown us that Venus's atmosphere is not just a passive envelope of gas, but an active, dynamic system with its own weather, its own seasons, despite the lack of axial tilt, and its own mysteries. Lightning might crackle through the clouds, though this remains controversial. Volcanic eruptions might occasionally inject fresh gases into the atmosphere, though we haven't caught one in the act. The polar vortices dance and swirl in patterns we're still trying to decode, and through it all, the atmosphere maintains its superrotation, racing around a planet that barely seems to turn at all. Scientists have observed that the rotation rate of Venus might not be perfectly constant, but could vary slightly over time. Measurements taken decades apart have shown small discrepancies that might indicate the rotation rate changes by a few minutes over periods of years or decades. These variations could be caused by exchanges of angular momentum between the atmosphere and the solid planet, by changes in the planet's moment, of inertia due to internal processes, or simply by measurement uncertainties. If real, these variations would provide valuable clues about the ongoing interaction between Venus's atmosphere and its interior. The idea that Venus's rotation rate might vary, even slightly, opens up fascinating possibilities. Perhaps the planet breathes rotationally, speeding up and slowing down in response to atmospheric or internal processes. Perhaps volcanic eruptions, by changing the mass distribution in the atmosphere or on the surface, can measurably affect the rotation. Perhaps the solar cycle, with its variations in solar wind and radiation, influences Venus's rotation through atmospheric interactions. These are subtle effects, at the edge of our ability to measure, but they remind us that planets are not static, unchanging objects but dynamic systems that continue to evolve. Pioneer Venus also carried a radar mapper that provided our first global view of Venus's surface topography. Though its resolution was much lower than Magellan's later maps, it revealed the basic structure of Venus's surface, the vast volcanic plains, the highland regions, the lack of obvious plate tectonic features. It showed us a world that was both similar to and profoundly different from Earth, a world shaped by volcanism and possibly by processes we don't see on Earth, like the formation of coronae and the peculiar tessera terrain found in some highland regions. Mariner 2, humanity's first successful interplanetary spacecraft, flew by Venus in 1962 and measured the planet's temperature for the first time, confirming that it was far hotter than Earth. This was a surprise to many scientists who had hoped Venus might be habitable under its clouds. Mariner 2 also found that Venus lacks a significant magnetic field, a discovery that would later be connected to its slow rotation and the absence of a dynamo in its core. These early measurements set the stage for all future Venus exploration, establishing the basic parameters that later missions would refine. Perhaps we are still learning how to listen to this world's rhythm, hearing what the light says when it returns to us slightly changed, carrying messages written in frequencies and phases, in Doppler shifts and polarizations. Each photon that bounces off Venus's clouds or penetrates to its surface and returns carries information, if only we know how to read it. The spectrum of reflected sunlight tells us about atmospheric composition. The polarization of scattered light reveals cloud particle sizes and shapes. The Doppler shift of radar echoes measures rotation rates and wind speeds. We're becoming better at reading these subtle messages, at extracting meaning from the whispers of light. And yet the pattern is kind, inviting us to wonder rather than worry. Venus doesn't threaten us with its backward rotation. It doesn't destabilize the solar system or endanger Earth. It simply exists as it is, following its own path, keeping its own time. In a universe that often seems chaotic and unpredictable, there's something comforting about Venus's steady backward turn, its reliable appearance as the morning or evening star, its constant presence in our sky and in our imagination. The study of Venus's rotation has led to advances in our understanding of planetary dynamics more generally. The mathematical techniques developed to analyze Venus's spin-orbit interactions have been applied to other planets, to moons, to asteroids, even to exoplanets orbiting distant stars. The computer models created to simulate Venus's atmospheric dynamics have improved our understanding of atmospheric circulation on all planets, including Earth. The instruments designed to study Venus have pushed the boundaries of what's possible in planetary exploration, leading to technologies that benefit other missions. Consider the engineering challenges of studying a planet like Venus. The surface pressure would crush most spacecraft like tin cans. The temperature would melt lead, destroy electronics, and degrade most materials within minutes. The sulfuric acid in the atmosphere would corrode exposed surfaces. The thick clouds block most wavelengths of light, making remote observation difficult. And yet, through ingenious engineering and careful mission planning, we've managed to study Venus in remarkable detail. Each mission has built on the successes and failures of previous ones, gradually expanding our ability to explore this hostile world. The radar mapping technique pioneered for Venus studies has revolutionized our ability to see through clouds and darkness. Synthetic aperture radar, the technology used by Magellan to map Venus's surface, is now used for Earth observation, allowing us to monitor deforestation, track ice sheet changes, and map the ocean floor. The heat-resistant electronics developed for Venus landers have applications in deep drilling, volcanic monitoring, and other extreme environments on Earth. The atmospheric entry technologies tested at Venus have informed the design of Mars landers and will be crucial for future missions to the outer planets. Scientists speak softly of torques, gentle twists, and of tides, not only in oceans but in air warmed by a considerate sun, and in rock heated by a planet's own internal fire. These torques are measured in tiny fractions of the planet's rotational energy, changes so small that they would be imperceptible over human lifetimes or even over the span of human civilization. But given millions and billions of years, these gentle twists can completely change a planet's rotation, can reverse its spin, can lock it into resonances, can create the kind of unusual rotation state we see in Venus today. Observations suggest that the atmosphere's daily breathing can share momentum with the planet, while the sun's pull, over ages, nudges the spin toward a tranquil balance. This balance is not a single point, but a region of phase space, a range of rotation rates and orientations that are quasi-stable over long periods. Venus might wander within this region, its rotation rate varying slightly as different forces wax and wane, but it remains trapped in the general backward rotating state by the combined effects of all the forces acting on it. Perhaps the core and mantle exchange their own quiet messages, coupling and uncoupling in rhythms we're just beginning to sense. The core of Venus, likely made of iron like Earth's core, might rotate at a slightly different rate than the mantle and crust. This differential rotation could generate friction, dissipating rotational energy and affecting the planet's overall spin rate. On Earth, the interaction between the core and mantle influences the length of our day by milliseconds over years. On Venus, with its much slower rotation, these effects might be proportionally larger, though still subtle by human standards. The question of whether Venus has a solid or liquid core remains open. Without a magnetic field, we can't be sure there's a liquid, convecting outer core like Earth has. But seismic data, which would definitively answer this question, requires landers that can survive on the surface for extended periods, something we haven't achieved yet. Future missions might deploy seismometers that could detect Venus quakes, if they occur, and use them to probe the planet's interior structure. Until then, we must infer what we can from the planet's gravity field, its rotation rate, and its lack of a magnetic field. Consider the possibility that chaos, over eons, can settle into a lullaby, a stable state that looks like backwardness but feels like rest. Chaos theory tells us that simple systems can produce complex behaviors, and complex systems can sometimes settle into simple patterns. Venus's rotation might have passed through periods of chaotic variation before settling into its current state. Or it might still be in a chaotic regime, with variations we haven't observed because our baseline of observations is too short. The mathematics of chaotic systems suggests that Venus's rotation could be sensitive to initial conditions, meaning that tiny differences in its early history could have led to vastly different rotation states today. In this view, Venus is not defiant. It is at peace with its own cadence, having found a rotation rate that balances all the forces acting on it. This is not a conscious choice, of course, but the result of physical laws playing out over cosmic time. It's the same kind of balance that rivers find when they carve their channels, that sand dunes find when they form their ripple patterns, that galaxies find when they settle into their spiral structures. Venus's backward rotation is just another example of nature finding an equilibrium, even if that equilibrium seems unusual from our Earth-centric perspective. The thermal structure of Venus's interior plays a crucial role in its rotation story. Heat from the planet's formation, supplemented by radioactive decay of elements like uranium and thorium, drives convection in the mantle. This convection might be different from Earth's plate tectonics, perhaps involving periodic overturning events where the entire surface is renewed in a relatively short time. These events, if they occur, could affect the planet's rotation by changing its moment of inertia, the distribution of mass that determines how easily it spins. Some scientists have proposed that Venus undergoes catastrophic resurfacing events every few 100 million years, where widespread volcanism renews much of the planet's surface. The evidence for this comes from the relatively uniform age of Venus's surface, as indicated by crater counts, and the lack of obviously old terrain. If such events occur, they would release enormous amounts of gas into the atmosphere, potentially affecting its mass and composition, which in turn could influence the atmospheric tides that help control the planet's rotation. The interaction between Venus's interior and its atmosphere might be more intimate than we realize. Volcanic gases don't just add to the atmosphere's mass, they can change its chemical composition, affecting how it absorbs and reflects sunlight, which influences the thermal tides. The atmosphere's pressure and temperature affect the stability of minerals at the surface, potentially influencing volcanic and tectonic activity. It's a coupled system where changes in one component can cascade through others, creating feedback loops that operate over geological timescales. Now imagine new eyes arriving with care, spacecraft designed with the patience of generations, built to withstand Venus's harsh embrace long enough to unlock its secrets. NASA's Da Vinci mission, planned for the 2030s, will descend through the clouds like a careful investigator, sampling the atmosphere's composition at different altitudes, measuring noble gas isotopes that can tell us about Venus's formation and evolution. As it descends, it will photograph the surface, providing our first high-resolution images of Venus's highlands, perhaps revealing details about their composition and formation that radar alone cannot provide. Da Vinci's descent sphere will be equipped with instruments that can measure the atmosphere's composition with unprecedented precision. It will look for trace gases that might indicate current volcanic activity, for isotope ratios that can tell us about the planet's water history, for chemical disequilibria that might hint at unknown processes. During its hour-long descent, it will experience the full range of Venus's atmospheric conditions, from the cold upper clouds to the furnace-like surface, gathering data that will help us understand how this thick atmosphere maintains itself and how it interacts with the planet below. NASA's Veritas mission, also planned for the 2030s, will map Venus with gentle precision, using advanced radar to create three-dimensional maps of the surface with resolution far exceeding Magellan's pioneering work. Veritas will measure the planet's gravity field in detail, revealing variations that tell us about the interior structure, about regions of different density that might indicate mantle plumes or variations in crustal thickness. It will also use infrared imaging to map surface composition, looking for recent volcanic flows that would still be warm enough to glow in infrared light. Veritas will also carry an instrument to measure Venus's rotation rate with unprecedented accuracy. By tracking surface features over time, it will be able to detect tiny variations in the rotation rate, perhaps confirming whether the planet's spin really does vary, and, if so, what causes these variations. This information will be crucial for understanding the ongoing interaction between Venus's atmosphere and its solid body, for testing models of atmospheric tides and core mantle coupling. ESA's Envision mission, scheduled to launch in the early 2030s, will listen for the planet's subtle heat, using a suite of spectrometers to map surface composition and search for signs of active volcanism. Envision will work in concert with Veritas, providing complementary observations that will give us a more complete picture of Venus than any single mission could provide. It will use radar to study surface changes, looking for evidence of current geological activity, and it will probe the atmosphere's structure and dynamics, adding to our understanding of the superrotation and its variations. Envision's subsurface radar sounder will peer beneath Venus's surface, potentially revealing buried structures that tell us about the planet's geological history. On Earth and Mars, subsurface radar has revealed hidden layers of ice and rock, ancient impact craters, and other features invisible from the surface. On Venus, it might reveal the structure of the volcanic plains, the depth of lava flows, or even ancient surfaces buried by more recent volcanism. These glimpses beneath the surface will add a third dimension to our understanding of Venus's geology. ISRO's Shukrayan-1, India's first mission to Venus, will add its steady gaze to this international effort to understand our sister planet. Planned for launch in the mid-2020s, it will carry instruments to study the atmosphere and surface, including a radar that will map the surface and clouds, spectrometers that will analyze atmospheric composition, and instruments to study how the solar wind interacts with Venus's upper atmosphere. Each mission brings its own perspective, its own strengths, and together they will provide a more complete understanding than any single nation could achieve alone. Scientists hope to measure the spin with finer patience, to hear the atmosphere's thermal tides and the planet's interior echoes with quieter instruments. The technology to survive on Venus's surface for extended periods is still being developed, with new high-temperature electronics and innovative cooling systems that might allow landers to operate for weeks or months instead of hours. Imagine seismometers listening for Venus quakes, weather stations monitoring the surface conditions over full day-night cycles, or even rovers exploring the highland regions where temperatures are slightly cooler. Perhaps we will find hints in tiny changes, a millisecond here, a murmur there, small truths that only long attention can reveal. The rotation rate might vary with the solar cycle, speeding up or slowing down as the sun's activity changes. It might respond to large volcanic eruptions, to shifts in atmospheric mass, to changes in the core mantle coupling. These variations, if we can measure them precisely enough, would be like windows into the planet's interior, revealing processes we can't observe directly. And yet we accept that some answers may remain open, like windows that look out on serene night. We may never know exactly how Venus came to rotate backward. The evidence from the early solar system has been erased by billions of years of geological activity. We can narrow down the possibilities, we can test hypotheses, we can build increasingly sophisticated models, but some aspects of Venus's history may remain forever uncertain. And perhaps that's as it should be. Mystery adds depth to knowledge, reminds us that understanding is always partial, always provisional, always open to revision. We keep looking, not to conquer the unknown, but to keep it company. Each mission to Venus is like a conversation with an old friend who still has secrets to share. We ask questions through our instruments, and Venus answers in the language of reflected radar, emitted infrared, scattered sunlight. Sometimes the answers are clear, sometimes they're ambiguous, sometimes they raise more questions than they resolve. But the conversation continues, patient and persistent, driven by curiosity rather than urgency. The study of Venus has taught us to be humble about our assumptions. We assumed Venus would rotate like Earth, and it doesn't. We assumed it might have conditions suitable for life, and it doesn't, at least not on its surface. We assumed we understood atmospheric dynamics, and Venus's superrotation challenged those assumptions. Each surprise has led to new understanding, not just of Venus, but of planets in general. Venus has been a teacher, sometimes harsh but always instructive, showing us the diverse ways that planets can evolve. Future missions might reveal even more surprises. Perhaps we'll discover that Venus's interior is more active than we thought, with ongoing plate tectonics of a different style than Earth's. Perhaps we'll find evidence of past oceans in the mineralogy of the highlands. Perhaps we'll detect biosignatures in the clouds, evidence of aerial life adapted to the acidic environment. Or perhaps we'll find that Venus is exactly what it appears to be, a cautionary tale of greenhouse warming, a world where the carbon cycle went in a different direction than Earth's, leading to a dramatically different outcome. The technology being developed for Venus exploration will have applications beyond that single planet. High-temperature electronics could be used to explore Io's volcanic regions or Mercury's sunlit side. Atmospheric entry systems tested at Venus could be adapted for missions to the gas giants. The techniques for seeing through thick atmospheres could be applied to Titan or to exoplanets with similar obscuring clouds. Venus is not just a destination, but a technological proving ground, pushing us to develop capabilities that will serve us throughout the solar system and beyond. What if, just maybe, Venus's backward spin is a reminder that physics is a story about patience, about how energy moves and rests, how systems settle into quiet arrangements over cosmic time. The laws of physics don't hurry, they don't have deadlines or schedules, they simply operate consistently and continuously, and given enough time, they can produce results that seem almost miraculous. A planet spinning backward, atmosphere racing around it, maintaining temperatures that would melt metal. These are not violations of physics, but expressions of it, demonstrations of what's possible within the framework of natural law. Data suggests that climate and spin can hold each other, like partners in a slow dance, a lesson we carry back to Earth with tenderness, not alarm. Earth's climate system is influenced by its rotation rate through the Coriolis effect, which helps drive ocean currents and atmospheric circulation. Changes in Earth's rotation rate, even tiny ones caused by earthquakes or melting ice sheets, can affect weather patterns. Venus shows us an extreme case of climate rotation coupling, where the atmosphere has possibly reversed the planet's spin. It's a reminder of how interconnected planetary systems are, how changes in one component can affect all others. Exoplanets too might wear such rhythms, their atmospheres guiding their turns under distant suns, and we listen for them with calm curiosity. As we discover more exoplanets, we're finding that many of them are unlike anything in our solar system. Hot Jupiters orbiting close to their stars, super-Earths with no solar system analogue, planets orbiting binary stars, each new discovery expands our understanding of what's possible. Some of these worlds might rotate backward like Venus, or sideways like Uranus, or in complex patterns we haven't yet imagined. Venus has prepared us for strangeness, taught us not to be surprised by diversity. The search for exoplanets has also given us new perspective on Venus. When we look at Venus-like exoplanets around other stars, we're seeing what Venus might look like from afar, what signatures it would show to alien astronomers, trying to understand it. The thick atmosphere would be detectable through transit spectroscopy. The high surface temperature would be evident in thermal emission. The lack of water vapor would be notable. These observations of exovenuses help us understand our own Venus better, providing context for its properties and evolution. Perhaps our place in this wide universe is to ask soft questions, to be present for the answers that arrive on their own time. We didn't choose when to discover Venus's backward rotation. That knowledge came when our technology was ready, when we could bounce radar off its surface and measure the Doppler shift. We didn't choose when to understand atmospheric superrotation. That understanding emerged gradually from decades of observations and theoretical work. The universe reveals itself at its own pace, and our role is to be ready, to be watching, to be listening when the answers come. In that presence, we feel connected, never alone. When we study Venus, we join a lineage of observers stretching back to ancient astronomers who first noticed the bright morning and evening star. Galileo, who first saw Venus's phases through his telescope, confirming that it orbits the Sun. Lomonosov, who first detected Venus's atmosphere during a transit. The engineers who built the spacecraft that visited Venus. The scientists who interpret the data. The students who will carry this knowledge forward. We're all part of the same endeavour, the same gentle quest to understand our cosmic neighbourhood. Venus connects us not just to the past, but to the future. The young scientists and engineers who will design the next generation of Venus missions are perhaps in school today, learning about physics and chemistry, dreaming about space exploration, the technologies that will finally allow us to maintain a permanent presence on Venus's surface. Perhaps floating cities in the more temperate cloud layers are being imagined in laboratories and workshops around the world. The questions we're asking today about Venus's rotation will be answered by future generations who will ask new questions we haven't thought of yet. The backward rotation of Venus has become a symbol in popular culture, a shorthand for the planet's alien nature. Science fiction writers have imagined civilizations that evolved with the backward sunrise, cultures whose mythologies and philosophies were shaped by living on a world that turns the wrong way. Artists have depicted the long Venus days and nights, the strange light filtering through the sulfuric clouds, the landscape that would look the same for months at a time as the sun crawled across the sky. Venus's backward spin has captured imaginations, becoming part of our collective understanding of the cosmos's diversity. But beyond symbolism and imagination, Venus's rotation matters scientifically. It affects the planet's interaction with the solar wind, potentially influencing atmospheric loss, rates. It determines the pattern of solar heating, which drives atmospheric dynamics. It influences the planet's internal dynamics, possibly affecting volcanic and tectonic activity. It might even have influenced the planet's habitability billions of years ago when conditions were different. Every aspect of Venus is connected to its rotation, making it not just a curiosity but a fundamental characteristic that shapes everything about the planet. The study of Venus's rotation has also contributed to our understanding of conservation laws in physics. Angular momentum, the rotational equivalent of linear momentum, must be conserved in any closed system. Venus's backward rotation represents a certain amount of angular momentum that must be accounted for. If Venus started rotating forward and now rotates backward, where did the angular momentum go? Into the atmosphere? Into orbital changes? Lost to space through atmospheric escape? These questions touch on fundamental principles that apply throughout the universe. As our observational capabilities improve, we're discovering that many astronomical objects have unexpected rotations. Some asteroids tumble chaotically. Some exoplanets are likely tidally locked. Some stars rotate so fast they're flattened into oblate shapes. Others rotate so slowly they're nearly perfect spheres. Venus's backward rotation is just one example of rotational diversity in the cosmos, but it's the example closest to home, the one we can study in greatest detail, the one that teaches us to expect the unexpected when we look at other worlds. The patience required to study Venus mirrors the patience of the planet itself. Venus has been rotating backward for billions of years and will continue to do so for billions more. Our brief moment of observation, these few decades of spacecraft exploration, are just an instant in Venus's long history. Yet in that instant we've learned so much, and we've realized how much more there is to learn. Venus teaches us patience, persistence, and humility, valuable lessons for any scientific endeavor. We return to the beginning with deeper ease. It's a question that seemed small, and yet it opened into a sky of gentle insights. Why does Venus rotate backward? The question led us to atmospheric dynamics, to planetary formation, to tidal forces, to the early solar system's chaos, to the patient work of time and physics. Each answer revealed new questions, each discovery opened new mysteries. The backward rotation of Venus is not a problem to be solved once and for all, but a phenomenon to be understood ever more deeply, a thread that, when pulled, unravels into the entire tapestry of planetary science. And yet the mystery continues, and that is beautiful, like a star that keeps us company as we fall asleep. We don't need to solve every mystery tonight. We don't need to have all the answers. Sometimes it's enough to wonder, to contemplate, to let our minds drift among the possibilities. Venus will keep turning its backward turn whether we understand it fully or not. The mystery will wait for us, patient and eternal, ready to reveal another layer whenever we're ready to look. Perhaps Venus's backward turn is less a problem to solve than a poem to read slowly, line by line, night after night. Each observation is a verse, each mission a stanza, each discovery a new interpretation of the meaning. We're not racing to the end of the poem, but savouring each line, each image, each metaphor that Venus offers. The backward rotation is the refrain that ties it all together, the recurring theme that gives the poem its structure and rhythm. In the quiet darkness, we remember that we are part of the story the cosmos tells itself, softly, without hurry. Our curiosity about Venus, our missions to study it, our patient observations and careful theories, these are all part of how the universe comes to know itself. Through us, the cosmos asks why Venus rotates backward. Through our instruments, it observes itself. Through our understanding, it comprehends its own nature. We are not separate from the cosmic story, but essential characters in it, the parts of the universe that have developed the capacity to wonder about other parts. The story of Venus's backward rotation is also a story about Earth, about what makes our planet special and what makes it typical. Earth rotates forward, but is that the normal state or the exception? Earth has a large moon that stabilizes its rotation, but is that necessary for habitability? Earth has plate tectonics and a magnetic field. but are those inevitable for Earth-sized planets or lucky accidents? By understanding Venus, we understand Earth better, seeing it not as the obvious template for planets, but as one possible outcome among many. The comparison between Earth and Venus extends beyond their rotations to their entire evolutionary histories. Both planets started with similar raw materials, similar distances from the Sun, relatively speaking, similar sizes and masses. Yet they diverged dramatically, one becoming a paradise for life, the other a hellish greenhouse. The backward rotation of Venus is perhaps both a symptom and a cause of this divergence, influencing and influenced by the different evolutionary path Venus took. Understanding this divergence helps us appreciate how special Earth is and how fragile its habitability might be. As we contemplate Venus's backward rotation from our forward-spinning Earth, we might wonder what it would be like to experience that different rhythm. Imagine standing on Venus's surface, protected by an impossibly strong suit, watching the sun rise in the west and climb so slowly across the sky that you could easily walk fast enough to keep it at the same position, creating an eternal noon or an eternal sunset. Imagine the psychological effect of days that last months, of a sun that moves backward through the sky, of a world where all our terrestrial intuitions about time and direction are reversed. But we don't need to stand on Venus to experience its rhythm. Every time we see it in our sky, bright and steady, we're seeing a world that turns to its own beat, that follows its own path, that reminds us of the diversity and wonder of the cosmos. Venus's light, reflected from those sulfuric clouds, has travelled millions of kilometres to reach our eyes, carrying with it the story of that backward-turning world. When we look at Venus, we're not just seeing light, we're seeing deep time, patient physics, and the beautiful complexity of planetary evolution. The ancient Greeks had two names for Venus because they didn't realize the morning star and evening star were the same object. In a sense, they were right to see it as two different things. Venus the morning star, herald of dawn, bringer of light, is psychologically different from Venus the evening star, follower of sunset, guardian of twilight. The backward rotation means that from Venus's surface, our sun would play these roles in reverse, setting in the morning and rising in the evening, another reversal of our earthly expectations. This duality of Venus, both morning and evening star, both Earth's twin, and Earth's opposite, both beautiful and hostile, captures something essential about the planet. It's a world of contradictions, of extremes, of conditions that challenge our understanding. The backward rotation is perhaps the perfect symbol for Venus, familiar yet alien, simple yet complex, understood yet mysterious. It's a rotation that makes sense within the laws of physics but defies our intuitions, that has explanations but retains its wonder. As we near the end of our contemplation of Venus's backward spin, let's remember that every end is also a beginning. Our understanding of Venus today builds on centuries of observation and decades of exploration, but it's also the foundation for future discoveries. The questions we can't answer today will inspire tomorrow's missions. The mysteries that remain will motivate new generations of scientists and engineers. Venus's backward rotation will continue to teach us, surprise us, and inspire us for as long as humans look up at the sky and wonder. The instruments we're developing today to study Venus will push the boundaries of what's possible. Quantum sensors that can detect minute gravitational variations, optical systems that can peer through thick atmospheres, electronics that can withstand extreme temperatures and pressures, materials that can resist acid corrosion for years. Each technological advance opens new windows into Venus's nature, allowing us to ask questions we couldn't even formulate before. The backward rotation that seemed like a simple fact becomes ever richer and more complex as our ability to study it improves. Future generations might establish floating cities in Venus's clouds, stationed at altitudes where the temperature and pressure are Earth-like. From these cloud cities, they could study the planet in ways we can only dream of today. They could drop probes to the surface regularly, maintain permanent monitoring stations, even attempt to modify the atmosphere to make the surface more habitable. For them, Venus's backward rotation wouldn't be a distant curiosity but a daily reality, something that affects their weather, their schedules, their entire way of life. Or perhaps we'll discover that Venus's backward rotation is more common than we thought. As we study more exoplanets, we might find that retrograde rotation is just as normal as prograde, that our Earth-centric view has biased our expectations. We might discover principles of planetary dynamics that make backward rotation inevitable under certain conditions, that explain not just Venus but a whole class of backward spinning worlds scattered throughout the galaxy. Venus would then be not an anomaly but an archetype, the first example of a common planetary type. The philosophical implications of Venus's backward rotation extend beyond astronomy and planetary science. It reminds us that nature doesn't conform to our expectations, that the universe is under no obligation to make sense to us, that reality is often stranger and more wonderful than our imagination. It teaches us humility, patience, and openness to possibility. It shows us that even in our own cosmic backyard, there are profound mysteries waiting to be explored, wonders that have been hiding in plain sight for all of human history. As we drift deeper into contemplation, we find ourselves at a crossroads where Venus's backward spin becomes more than just a planetary quirk. It becomes a mirror for understanding our place in the cosmos. The way Venus turns, patient and contrary, speaks to something fundamental about how worlds can be, about the vast range of possibilities written into the laws of physics. Every planet is an experiment in what matter and energy can become when given billions of years to settle into patterns, and Venus's experiment yielded this beautiful oddity, this backward dance that continues night after night, age after age. The mathematics that describe Venus's rotation are the same mathematics that describe the spiral of galaxies, the orbit of electrons around atomic nuclei, the flight of birds in formation. Angular momentum, torque, resonance. These concepts scale from the quantum to the cosmic, creating patterns that repeat across every level of reality. When we understand why Venus rotates backward, we're understanding principles that apply everywhere in the universe, from the smallest particles to the largest structures. It's a reminder that despite the universe's vastness and complexity, there are underlying unities, fundamental principles that connect everything to everything else. Consider how our understanding of Venus's rotation has evolved with our technology and theoretical frameworks. Ancient astronomers could only track its position in the sky. Galileo could see its phases. 19th century astronomers could measure its orbit precisely. 20th century scientists could bounce radar off its surface. 21st century missions can map its surface in 3 dimensions, analyze its atmosphere layer by layer, and model its interior structure. Each generation has added layers to our understanding, like an artist adding glazes to a painting, each translucent layer adding depth and richness to the whole. The story of Venus's exploration is also a story of international cooperation and competition, of the human drive to explore and understand. Soviet and American spacecraft raced to Venus during the Cold War, each nation pushing the boundaries of what was possible, sharing their discoveries with the world even as they competed for firsts. European, Japanese, and Indian missions have added their perspectives, their instruments, their questions. Venus has become a meeting ground for humanity's collective curiosity, a place where our species comes together in the pursuit of knowledge. When we think about Venus's backward rotation in the context of Earth's climate crisis, it takes on new relevance and urgency. Venus shows us what can happen when greenhouse gases accumulate unchecked, when positive feedback loops amplify warming, when a planet's climate system shifts into a new state. The backward rotation might have played a role in this transformation, affecting how heat was distributed, how the atmosphere evolved, how the planet lost its water. Understanding Venus helps us understand the boundaries of habitability, the tipping points that can transform a living world into a dead one. But Venus also gives us hope in unexpected ways. It shows us that planets are resilient, that they can survive extreme conditions, that they continue to evolve even after catastrophic changes. Venus didn't stop being a dynamic world when it lost its oceans and developed its crushing atmosphere. It found a new equilibrium, harsh by our standards but stable by its own. It continues to have weather, possibly volcanism, a complex atmosphere with its own beauty and logic. Life as we know it couldn't survive there, but Venus itself survives, persists, continues its backward turn through the eons. The backward rotation of Venus challenges us to think about time differently. On Earth, we're used to days and years having a certain relationship, to sunrise and sunset following a predictable pattern. Venus shows us that these patterns we take for granted are just one way time can be structured on a planet. The 117-day solar day, the 243-day sidereal day, the 225-day year, These create a temporal landscape unlike anything on Earth, a rhythm that would reshape any biology, any psychology, any culture that evolved within it. Imagine future humans, perhaps centuries from now, who have adapted to life in Venus's cloud cities. For them, the backward rotation wouldn't be backward at all. It would simply be the way their world turns. They might develop calendars based on the atmospheric superrotation, marking time by the 4-day cycle of clouds rather than the slow solar day. They might have festivals celebrating the rare moments when Earth is visible in their sky, a blue star that reminds them of humanity's origin. The backward rotation that seems so strange to us would be the foundation of their entire temporal experience. The question of whether Venus ever had life and whether its backward rotation played a role in life's absence or extinction adds another dimension to our contemplation. If Venus once had oceans, as some evidence suggests, those oceans would have experienced tides very different from Earth's, driven primarily by the sun rather than a moon, and affected by the planet's rotation rate. As the rotation slowed and possibly reversed, these tidal patterns would have changed dramatically. Any life that had evolved in those ancient oceans would have had to adapt to changing rhythms, changing days and nights, changing seasons of a sort we can barely imagine. Some scientists have speculated about the possibility of life in Venus's clouds today, microorganisms that might inhabit the temperate layers of the atmosphere. If such life exists, it would experience the 4-day cycle of the super-rotating atmosphere rather than the planet's slow backward turn. These hypothetical organisms would know nothing of solid ground, nothing of the surface far below. For them, existence would be an eternal flight through acidic clouds, riding winds that race around a planet they never see. The backward rotation would be irrelevant to their experience, a fact about their world that affects them only indirectly through the atmospheric dynamics it influences. The search for life on Venus, whether past or present, connects to larger questions about life in the universe. If life could arise on Venus and then be extinguished by changing conditions, how common is this story throughout the cosmos? How many worlds have seen life emerge and then disappear, leaving only subtle chemical signatures in their atmospheres or mineralogical hints in their rocks? Venus might be teaching us that life is more fragile than we thought, or perhaps that it's more resilient, able to persist in clouds when surfaces become uninhabitable. As we contemplate these possibilities, we're reminded that Venus's backward rotation is just one thread in a vast tapestry of cosmic evolution. Every feature of Venus, its rotation, its atmosphere, its surface, its interior, is connected to every other feature through complex feedback loops and historical contingencies. The planet we see today is the product of 4.5 billion years of evolution, of countless events and processes that have shaped and reshaped it. The backward rotation is both a cause and an effect in this complex history, influencing and influenced by everything else. The study of Venus has taught us to be careful about our assumptions, to question what seems obvious, to look deeper than surface appearances. We assumed Venus would be Earth-like because of its similar size and neighbouring position, but it turned out to be profoundly alien. We assumed its clouds might hide a tropical paradise, but they hide a furnace. We assumed it would rotate like Earth, but it doesn't. Each wrong assumption led to learning, to a deeper appreciation of planetary diversity, to better questions and better understanding. This process of being wrong and then learning from our wrongness is perhaps the most human aspect of science. We approach the universe with our Earth-trained intuitions, our human-scale experiences, and the universe consistently surprises us with its actual nature. Venus's backward rotation is a perfect example of this surprise, this reminder that cosmos doesn't conform to our expectations. But rather than being discouraged by our wrong assumptions, we're inspired by them, driven to understand why reality differs from our expectations, to expand our intuitions to encompass the actual universe rather than our imagined one. The instruments we point at Venus, from ground-based telescopes to orbiting spacecraft, are extensions of our senses, allowing us to perceive what our bodies cannot. Through them, we feel the temperature of Venus's surface, taste the chemistry of its clouds, hear the echoes of a radar bouncing off its mountains. These technological senses have revealed the backward rotation, and so much more, expanding our sensory world to include phenomena far beyond human scale. In a very real sense, when we study Venus, we're expanding what it means to be human, adding new dimensions to our experience of reality. The data streaming back from Venus missions becomes part of humanity's collective memory, archived in databases that future generations will access and analyze with tools we haven't invented yet. Every measurement of Venus's rotation rate, every image of its surface, every spectrum of its atmosphere becomes part of this permanent record, this growing encyclopedia of cosmic knowledge. The backward rotation of Venus is now written into humanity's memory, as surely as our myths and histories, part of the story we tell about the universe and our place in it. But data alone doesn't create understanding. It takes human creativity, intuition, and patience to transform measurements into meaning, to see patterns in the noise, to connect disparate facts into coherent theories. The scientists who study Venus's rotation bring not just their technical knowledge, but their full humanity to the task, their curiosity, their aesthetic sense, their ability to imagine and wonder. The backward rotation of Venus is understood not by computers or equations alone, but by human minds engaging with mystery, bringing all their faculties to bear on questions that have no easy answers. The metaphors we use to understand Venus's rotation reveal as much about us as about the planet. We speak of Venus dancing backward, of the planet remembering its past, of forces conspiring to reverse its spin. These anthropomorphic descriptions aren't scientifically precise, but they help us relate to phenomena far outside human experience. They transform abstract physics into something we can feel and imagine, something that resonates with our embodied understanding of the world. The backward rotation becomes not just a fact but a story, not just data but meaning. As our night journey continues, we find ourselves floating in that space between knowledge and mystery, between what we understand and what we're still discovering. Venus turns below us, patient in its backward rotation, neither hurrying nor slowing, simply being what billions of years of cosmic evolution have made it. There's a peace in this patience, a reminder that the universe unfolds at its own pace, indifferent to human urgency. Venus will still be rotating backward long after our civilization has passed into history, long after our sun has swollen and consumed the inner planets, long after the last stars have formed and the universe has settled into its final configuration. Yet knowing this doesn't diminish the importance of our brief moment of observation and understanding. In fact, it makes it more precious. We are the universe's brief experiment in consciousness, its momentary ability to observe and understand itself. Through us, the cosmos knows that Venus rotates backward, wonders why, and searches for answers. This knowledge, however temporary in cosmic terms, is profound in its implications. It means the universe has achieved self-awareness, however limited and localized that awareness might be. The backward rotation of Venus connects to fundamental questions about determinism and chance in the universe. Was Venus destined to rotate backward from the moment of its formation, its fate sealed by the initial conditions of the solar system? Or was it a chance event, a random collision or gravitational interaction that could have gone differently? These questions touch on deep issues in physics and philosophy, whether the universe is fundamentally deterministic or probabilistic, whether the present was inevitable from the past or whether genuine novelty can emerge. Modern chaos theory suggests that even in a deterministic universe, tiny differences in initial conditions can lead to vastly different outcomes. Venus's backward rotation might be the result of such sensitive dependence, a cosmic butterfly effect where an infinitesimal difference 4.5 billion years ago led to a planet spinning the wrong way today. If we could rerun the formation of the solar system with slightly different initial conditions, would Venus still rotate backward? We'll never know, but the question itself enriches our understanding of causation and possibility. The way we study Venus's rotation through patient observation, theoretical modelling, and technological innovation exemplifies the scientific method at its best. We observe phenomena that puzzle us. We develop hypotheses to explain them. We test these hypotheses with new observations and experiments, and we refine our understanding based on the results. The backward rotation of Venus has been subjected to this process for decades, and our understanding has gradually improved, even as new mysteries have emerged. It's a perfect example of science as a self-correcting, ever-improving approximation of truth. But science is not the only way to engage with Venus's backward rotation. Artists have been inspired by it, poets have written about it, Musicians have composed pieces that try to capture its strange rhythm. The backward spinning planet has become a cultural symbol, a metaphor for going against the grain, for being different, for finding your own path. In this way, Venus's rotation has transcended its astronomical significance to become part of human culture, part of how we think about individuality and conformity, about tradition and innovation. Children learning about the solar system often find Venus's backward rotation one of the most memorable facts, something that sticks in their minds long after they've forgotten other details. There's something captivating about a planet that does things differently, that breaks the rules, that reminds us that nature is full of surprises. For many, Venus's backward rotation is their first encounter with cosmic diversity, their first hint that the universe is stranger and more wonderful than they imagined. It plants a seed of curiosity that might grow into a lifelong interest in science, in exploration, in understanding. The backward rotation also raises questions about what we mean by backward and forward in the first place. These are human concepts based on our experience on Earth, our arbitrary decision to call Earth's rotation direction forward. From a cosmic perspective, there's no preferred direction of rotation. Venus isn't really rotating backward. It's just rotating in a direction opposite to Earth's. The universe doesn't care about our definitions and categories. It simply is, and our job is to observe and understand it on its own terms, not force it into our preconceptions. This lesson in perspective applies beyond astronomy. How often do we judge things as wrong or backward simply because they differ from what we're used to? How often do we miss beauty or wisdom because it comes in unexpected forms? Venus's backward rotation teaches us to question our assumptions, to be open to different ways of being, to recognize that diversity is not deviation but richness. It's a lesson in cosmic humility that has applications in every aspect of human life. As we approach the end of our contemplation, let's consider what Venus's backward rotation might mean for the far future. As the sun ages and brightens, Earth will eventually become too hot for life, entering its own greenhouse phase. Billions of years from now, Earth might resemble present-day Venus, with a thick atmosphere and scorching surface. Will Earth's rotation be affected by these changes? Will future astronomers on distant worlds observe Earth and wonder why it rotates the way it does, just as we wonder about Venus today? The ultimate fate of Venus's rotation is tied to the fate of the solar system itself. As the sun loses mass through its solar wind, the planet's orbits will slowly spiral outward. Tidal interactions will continue to exchange angular momentum between planets and the sun. Given enough time, far more than the sun's remaining lifetime, Venus's rotation might change again, perhaps speeding up, perhaps reversing once more. But these are changes that will play out over cosmic timescales, long after humanity and Earth itself have passed into cosmic history. Yet even knowing our observations are temporary, even knowing that Venus's backward rotation is just a passing phase in the endless evolution of the cosmos, we find meaning in our study of it. We are here now, conscious and curious, able to wonder at Venus's backward turn. This moment of understanding, however brief in cosmic terms, is infinitely precious because it's the only moment we have. We are the universe's way of knowing itself, and through us, it knows that Venus rotates backward, knows the questions this raises, knows the beauty of the mystery. The journey we've taken tonight, from Earth to Venus and back, from present to past to future, from observation to speculation to philosophy, mirrors the journey of science itself. We start with simple observations. Venus rotates backward, and follow them wherever they lead, through physics and chemistry, through time and space, through knowledge and mystery. Along the way, we discover not just facts about Venus, but truths about the universe and our place in it. We learn that we are connected to everything, that our curiosity is cosmic curiosity, that our wonder at Venus's backward rotation is the universe wondering at itself. In the quiet darkness, as we complete our contemplation of Venus and its patient backward turn, we can feel how this knowledge settles into us, becoming part of our understanding of the world. We'll never look at Venus the same way again. When we see it shining in the morning or evening sky, we'll remember its backward rotation, its slow days, its racing atmosphere. We'll remember that it's a world utterly unlike Earth, yet formed from the same cosmic materials, shaped by the same physical laws, sharing the same solar system. We'll remember that its differences are not flaws but features, not mistakes but variations on the theme of what a planet can be. The backward rotation of Venus has become more than an astronomical fact for us tonight. It's become a meditation on time and change, on patience and perspective, on the beauty of diversity and the wonder of discovery. It's reminded us that the universe is larger and stranger than we can fully grasp, but that the attempt to understand it is one of the most human things we can do. It's shown us that even in our cosmic backyard, there are profound mysteries waiting to be explored. Questions that lead to questions that lead to questions, each answer opening new doors of wonder. As you lie there, perhaps drowsy now, perhaps drifting towards sleep, you can carry with you the image of Venus turning its slow backward turn through space. There's something deeply peaceful about that image, something that transcends the violence of Venus's surface conditions or the mystery of its reversed rotation. It's the peace of cosmic time, of processes that unfold over billions of years, of a universe that's in no hurry to reveal all its secrets. Venus will keep rotating backward whether we're watching or not, whether we understand it or not, a constant in the cosmos that reminds us of scales beyond human comprehension. Tomorrow when you wake, the world will seem a little different knowing what you now know about Venus. The morning star or evening star, if visible, will carry new meaning. The sunrise coming from the east as always on Earth will remind you that on Venus it would come from the west. The 24-hour day we take for granted will seem precious knowing that on Venus a day lasts 243 times longer. These shifts in perspective, subtle as they are how scientific knowledge changes us, expands us, makes us more than we were before. The children who learn about Venus's backward rotation today might be the ones who finally solve its mysteries tomorrow. They might develop new theories we haven't imagined, build spacecraft that can survive indefinitely on Venus's surface, or even find ways to terraform Venus, to give it back its oceans and breathable atmosphere. For them, Venus's backward rotation won't be an ending but a beginning, not a final answer, but a first question that leads to lifelong curiosity about the cosmos. But tonight, for us, Venus's backward rotation is a lullaby, a gentle reminder that the universe is vast and mysterious and beautiful, that there are wonders all around us if we just know how to look. As sleep approaches, we can let go of the need to understand everything, to solve every mystery, to answer every question. We can simply rest in the knowledge that Venus is out there, turning backward, patient and eternal, a companion in our journey through the cosmos. The story of Venus's backward rotation is far from over. New missions will reveal new details, new theories will explain old observations, new questions will emerge from new answers. The conversation between humanity and Venus will continue as long as we keep looking up, keep wondering, keep exploring. Each generation will add its chapter to the story, its contribution to the understanding, its questions to the ongoing dialogue. Venus's backward rotation will continue to teach, to inspire, to mystify. As we close our eyes and drift towards sleep, we can feel ourselves still floating in that imaginary space between Earth and Venus, between the known and unknown, between waking and sleeping. Venus continues its backward rotation below us, Earth continues its forward rotation behind us, and we float between them, consciousness suspended between two worlds, two ways of being, two cosmic possibilities. In this space, we don't need to choose sides or decide which is right. We can simply appreciate both, marvel at the diversity, wonder at the beauty of it all. Perhaps in our dreams tonight, we'll visit Venus, protected by imagination from its harsh reality. We'll stand on its surface and watch the slow, backward sunrise, feeling the weight of its dense atmosphere, seeing the landscape unchanged for millions of years. Or perhaps we'll float in its clouds, riding the super-rotating winds, seeing the planet from a perspective no human has yet achieved. In dreams, we can experience Venus's backward rotation not as an abstract fact, but as a lived reality, feeling in our dream bodies what it might be like to inhabit a backward-spinning world. But even in waking life, we now carry a piece of Venus with us. The knowledge of its backward rotation has become part of our mental model of the universe, part of how we understand our cosmic neighborhood. We're richer for this knowledge, expanded by it, made more cosmopolitan in the truest sense, citizens not just of Earth, but of the solar system, aware of our neighboring worlds and their wonderful peculiarities. Venus's backward rotation is now part of our story, and we're part of its story, the conscious observers who noticed, wondered, and sought to understand. The ancient astronomers who first tracked Venus across the sky couldn't have imagined that one day their intellectual descendants would discover its backward rotation, would send spacecraft to study it, would write symphonies of words trying to capture its mystery. Yet their observations laid the groundwork for everything that followed. In the same way, our observations and wonderings today lay groundwork for future discoveries we can't imagine. We're links in a chain of curiosity that stretches from the past into the future, each generation adding its contribution to humanity's growing understanding of the cosmos. Venus's backward rotation reminds us that we live in a universe of endless surprises, where even our nearest neighbours can confound our expectations. It reminds us that there's always more to learn, always new mysteries to explore, always reasons to keep looking up. It reminds us that diversity is not an exception but the rule, that every world has its own way of being, its own story to tell, and it reminds us that we're fortunate to live in an age where we can know these things, where we can reach out with our instruments and our imagination to touch other worlds, to learn their secrets, to add their stories to our own. As sleep finally takes hold, as consciousness fades into dreams, we can release our grip on understanding and simply rest in wonder. Venus rotates backward, and that's enough to know for tonight. The mystery will still be there tomorrow, still inviting investigation, still offering its gentle challenges to our earthbound assumptions. But for now, in this moment between waking and sleeping, we can simply appreciate the beauty of a universe where planets can rotate backward, where every world is unique, where mystery and wonder are woven into the very fabric of existence. We close our eyes, breathing slowly and deeply, feeling ourselves part of the great cosmic dance where some partners turn one way and others turn another, where the music of the spheres includes notes we're still learning to hear. Venus turns backward through our dreams, patient and eternal, a reminder that the universe is larger than our imagination, stranger than our theories, more beautiful than our words can capture. And in that turning, in that patient backward rotation through the darkness, we find a peace that carries us gently into sleep, into dreams where anything is possible, even backward spinning worlds that challenge everything we thought we knew. The last thought before sleep claims us completely is not a question or an answer, but a simple acknowledgement. Venus rotates backward. We don't fully understand why, and that's perfectly okay. The mystery is as beautiful as any solution could be. The journey of discovery is as important as any destination, and the universe, with all its backward-spinning Venuses and forward-spinning Earths, with all its diversity and mystery and wonder, is exactly as it should be. Complex beyond comprehension, beautiful beyond description, and patient beyond measure, turning in the darkness, waiting for us to understand, one small mystery at a time. Good night, and sweet dreams of backward-turning worlds and the cosmic dance that connects us all.